Swayam Prabha. Digital India. Educated India.
With discontinuous conduction. So when we have discontinuous conduction, the equations definitely become somewhat complex. They are not really as simple as what it had been so far. So we are looking at the buck converter again. I'm going to have essentially a switch here which is in series, and then I'm going to have a diode, then I'm going to have an inductance, a capacitance and a load. Right? So we said that when the switch is on, we are going to have inductance accumulating energy. Maybe we have not kept the switch on for long enough so that the inductance energy could be accumulated, so that it can drive the current for the entire of duration, or maybe the input voltage is not large enough. That is also a possibility. Or the inductance is not large enough. Any one of them, whatever is the case. Maybe I'm going to have otherwise the resistance to be very large. If the resistance is large, then also the current will be small. So if the load is large, or the input supply voltage is small, or the inductance value is not large enough, or I have not kept it on for quite a long time, duty ratio is not large enough, the inductance stored energy will become pretty small in that case. So if I actually look at the inductance waveform, current waveform, I expect that generally the current should start from a non-zero value, but it may not start from a non-zero value because the inductance is not having sufficient stored energy. So I may have the inductance current rising like this, and it may fall down quickly. And still there is time for the switch to be fired again. So which means I am not going to have this to be completely equal to T off, rather my T probably is going to be longer than this. So what I am having is, this is dt, this is d1 times t, which is not 1 minus d. d1 is less than 1 minus d. So I am not going to really have the inductance continue to conduct for the entire of duration because the energy is not sufficient enough. Only this much is going to be my d1t. So under this condition, I have to write during on interval. We wrote this earlier also, V in minus V naught, right? That is what was VL. So this multiplied by dt equal to L delta IL, right? And we are going to have actually the other condition. What I have is, whatever is my V naught, that is equal to VL. That's what we said. So previously we wrote this as V naught multiplied by 1 minus d times t. Now I can't write that because it is not conducting for the entire duration. So I have to write this as V naught multiplied by d1t is equal to, actually this is going to be L delta IL, where I'm going to have d1 less than 1 minus d, right? So now I have to equate these two. So I should say V in minus V naught multiplied by dt equal to V naught into d1t. So I can write this is V naught into d plus d1 equal to V in into d. So V naught divided by Vn is going to be equal to d divided by d plus d1, right? When it was continuous conduction, d1 was equal to 1 minus d. That's why we could get d divided by 1. So it was simply d times V in equal to V naught, right? So you have to actually look at how to solve for this d1. Will we be able to solve for d1? So if I am actually looking at what is the inductance average current in this particular case, that will be same as I naught. So get what is IL average, and then that can be solved for by actually solving this, right? This is essentially what is the area under this curve. This is Imax or delta IL, whatever it is. So delta IL multiplied by half multiplied by d plus d1 multiplied by t, right? This is essentially your area under that triangle. That has to be averaged over t. This will be IL average or I naught. And I naught is equal to V naught by R. Right? So I can write V naught in terms of d by d plus d1 and so on and so forth. But I should be able to get a quadratic equation in d1 ultimately, which I can solve for. I want you guys to do that. Please do it. You guys will do that as a homework. Get this again equated in terms of d and d1, and then you will be able to get ultimately a quadratic equation in terms of d1. So get a quadratic equation in terms of d1. D I already know, d1 is the one which I have to solve for. So d1 can be expressed in terms of, you will have d, f, r and so on. These things will be, there in the equation. You would be able to arrive at what is the d1 value. So that gives you a complete closed form expression for the input-output relationship. So when you solve a problem in the buck converter, for example, if you find that the inductance current ultimately is going to negative for a given value of inductance, for a given value of duty ratio, for a given value of V in, V naught and R, if you are getting the inductance current to be going in the negative direction, then you know that it is actually getting into discontinuous conduction, because inductance current cannot go in the negative direction in the DC-DC converter. The moment you get a negative current, then you know it is going into actually the discontinuous conduction mode. So at that point, you should be able to actually solve for D1 by using whatever you are going to derive as the quadratic equation. From that, you would be able to derive the expression for D1, which you will be able to solve for. Once you get that, then the rest of the things will be, directly possible for you to arrive at all the relationships. Not a problem at all. Okay? So whenever you actually are given a problem, first of all, you have to make sure that it is in continuous conduction mode. If it is not in continuous conduction mode, you cannot use the expression whatever we derived earlier. One way of doing it is, maybe you can check what is L critical value. You have that expression. And if the inductance given is actually smaller than L critical, you know it has already been in discontinuous conduction mode for the given operation. And then you can calculate what is D1 and so on and so forth. So you can do it either way. Either you first of all solve for inductance current, or you solve for what is the inductance value, and then you try to see whether it is above critical conduction mode or below critical conduction mode. Right? We have one more converter in non-isolated category again, which is known as Cooke converter or CUK, however you may pronounce the name. Generally many people call it as Cooke converter. So Cooke converter is extensively used in many applications, because of which I would definitely like to take that up as well. But what I was thinking is I'll look at non-isolated converter first, and then if how many classes are left over I'll check, and then accordingly I'll take Cooke converter, or I will not take Cooke converter. So we will try to look at that as well. But before that, I would like to go in for isolated DC-DC converters. So in isolated DC-DC converters, the major difference is that I'm going to have a transformer. Invariably, I will have a high frequency transformer, which will be isolating between the input side and output side. There will be a high frequency transformer which will be used for isolating the input side from the output side, which is needed in many of the cases. Because for example, if you look at your computers where we are using SMPS, in those cases, what we give it to the ICs, they are all 5 volts, 3.3 volts, 12 volts and so on. Whereas what we give from the UPS is 230 volts. So the power ground and the ground of the electronics, we would not like to connect them together. Unless we have a transformer in between them, you know, we will not be able to provide isolation between the ground of the power side and ground of the electronic side. So that is one reason why most of the switch mode power supplies will use a transformer. You can very well use 50 Hertz transformer as well. Normally what you have as regulated power supply in your laboratory, what is done normally is, so in a linear regulated power supply versus SMPS, I would like to show the difference. In the linear regulated power supply, normally most of the times what is done is, I'm going to use a 50 Hertz transformer right up front. So an isolation is provided there also. In most of the linear regulated power supply, I will have isolation, but it will be a 50 Hertz transformer normally. So what I have is 230 volts. I will step it down to 5 volts or 15 volts or something of that sort, depending upon what is the kind of output I require. If it is a regulated power supply with 12 volts, I may have 230 by 15 volts transformer. Now whatever is the output of this transformer, so this is a 50 Hertz transformer. Now the output of this transformer is going to be rectified in all probability with the help of a simple diode bridge rectifier. This diode bridge rectifier's output will be given to a voltage regulator. The voltage regulator is generally a transistor working in active region. So if it is working in active region, VCE is not minimum. VCE value is going to be fairly large depending upon how much is the base drive that we are using. So it is not like the IGBT or MOSFET that we use in power electronics, where it will be completely into saturation or completely in cutoff region. Whereas here it is going to be in active region. So we will have a transistor. So this is generally a voltage regulator IC which will be used. This will be basically a transistor in active region. So which means it is going to drop a huge amount of voltage. So 15 volts, when I probably use the full wave rectifier, I will get about 14 volts or something. So 2 volts, 3 volts, something will be dropped. If I want 10 volts, almost 4 volts are going to be dropped. So it is also carrying full current. So you can imagine the copper losses that take place within this small transistor. A huge amount of copper losses will take place, because of which I had to put a large heat sink. The heat sink that I'm going to put for this regulator IC, if you ever put your hands on that regulator IC, you will get a burn normally. It will be really, really hot because of a huge amount of copper losses that is taking place. Now, whatever is the output now, this will be regulated voltage. Inside the voltage regulator IC, there will be mainly two components. One will be a transistor in active region, another will be a Zener diode. The Zener diode will normally maintain what is the reference voltage I require, and there will be some kind of comparison between that Zener diode voltage and the actual output voltage. And then that, whatever is the difference, that will go as the drive. That will set the drive value, base drive value for the transistor. So it will be driven, as per whatever is the error voltage that is available. So the more the error, the more probably I'll have to drop as the voltage, and then, the more will be the copper loss and so on and so forth. So the voltage regulator is supposed to maintain the output voltage as a constant irrespective of any supply voltage variation, because understand that this is not 230 volts always, although we say it is 230 volts. It may be 180 at some point, it can be 260 at some point. So what I get as the voltage here is unregulated. So we regulate this with the help of this voltage regulator IC. So the major problem with linear regulated power supplies is twofold, or I would say three. One is I am not going to be able to reduce the copper losses, which means efficiency is generally low. I will not have good efficiency. This is one problem. The second problem that I normally would face with this is, because of the 50 hertz transformer here, it is going to be bulky. You guys remember the transformer equation. E is proportional to 4.44 F, phi and number of turns. Right? This is what we derived as the transformer voltage equation. So I can say flux is proportional to E by F, or voltage divided by F. E is approximately equal to V. So if I am talking about a 230 volts 50 hertz transformer, if the flux happens to be, let us say, 2 Weber, for example, when I talk about the same 230 volts but maybe 50 kilohertz transformer, the flux will be 2 into 10 power minus 3 Weber. Right? The flux will decrease tremendously when I talk about larger frequency transformers. So, if I talk about a particular material which can have a flux density of 1.2 Weber per meter square, if I use that material for 50 hertz transformer vis-a-vis, if I use the same material for a 50 kilohertz transformer, I can really make very, very small cross-sectional area for my core of the transformer. So obviously, because the flux requirement decreases with increase in frequency, the transformers would get miniaturized. They will become really, really tiny when I go for larger and larger frequencies. That is one reason why I think I mentioned this definitely in electromechanics class. Aerospace electronic systems or aerospace machines generally, whatever is used in aircrafts, they all operate at 400 hertz. They never operate at 50 hertz. Okay, so it is like a trade-off. You don't want too much of inductive reactance to come into picture in the machine as the drop, leakage reactance, vagera. You don't want too much, but you don't want very bulky machines also. So it is like a trade-off. They have arrived at 400 Hertz as a standard for aerospace machines, generally aircraft machines in the aircraft. So when we talk about linear regulated power supply, the transformers become bulky because they are operating at 50 Hertz, right? So if we try to operate it at a higher frequency, like using a DC-DC converter and use a high frequency transformer, like what we do in the case of SMPS, that's why SMPS is really tiny. If you look at many of the computer power supply, they'll be really tiny because of high frequency link coming into picture somewhere. The third disadvantage of linear regulated power supply is generally for every output, I may use independently 3 regulator ICs and so on and so forth. Whereas when I use the high frequency transformer towards the output, if I try to use it towards the output side, the primary may have a particular voltage. I can have multiple secondaries. One can feed 5 volts, one can feed 12 volts, another one can feed minus 12 volts, the fourth one can feed 3.3 volts and so on. So SMPS generally will have single primary and multiple secondary in the high frequency transformers that are used at the end. Because of which I would be able to get multiple outputs from a single input feeding line, whereas that doesn't happen most of the times in linear regulated power supplies. So here I would be able to obtain multiple outputs stiffly regulated. I can regulate them very stiffly. That's not a problem, because the DC-DC converter, what I use actually in this particular case, I will be able to turn on and turn off. From saturation region I can go to cutoff and back, because of which there will not be much of copper losses, so efficiency is good. And I would be able to use high frequency transformer, so it will be tiny and it will save on space. And the third one, what I have is basically, multiple output I'll be able to obtain by having multiple secondaries, right? So we would be looking at, so SMPS, if I try to show basic diagram, it will have basically 230 volts, from which I may have a diode converter. And what I have here as the output will be of the order of maybe 230, 220 volts if I don't put a capacitor. If I put a high value capacitor, then it will charge up to the peak. If I don't put a capacitor, this output will be given to an isolated DC to DC converter. So at the output of the isolated DC-DC converter, normally we will have a transformer. So I may have single primary at the output of the isolated DC-DC converter with multiple secondaries. Right? So this will give output 1. Of course, if I am talking about a high frequency transformer, what I get as the output here may be AC. If I have to convert that into DC, that rectifier is also part of isolated DC-DC converter. I am showing it explicitly because I wanted to show the high frequency transformer. So this is the high frequency transformer, and the output normally will have a center tap rectifier, something like this. So I am going to have 2 diodes and the load is connected between these 2 terminals. This is a center tap rectifier, what we initially started with. Normally we will use a center tap rectifier in the power supply so that only one diode will conduct at a time, the drop will be smaller. Of course, there are multiple stages, but we are going to operate this converter only in either on or off. So on-off control we will be using. So we will not have much of losses in this particular converter. So this is the way normally SMPS is constructed. So we will go into isolated DC-DC converter in the next class. Thank you.